Hello friends, welcome back to my channel. Today in this video I'll be discussing one numerical that is based on diffusion through solids. In my last video I have discussed diffusion through solids that follows Fick's law. Under that I have discussed three cases. One was steady state diffusion through solid slab. Second was steady state diffusion through the wall of a cylinder, and the third one was steady state diffusion through the wall of a spherical shell. So based on this discussion we will solve two numericals. Out of that, the first numerical we are going to solve in this video, and the second numerical I will be discussing in my next video. Those of you who have not yet seen my last video and my some earlier videos, you please subscribe to my channel and watch all those videos. Hit the bell icon so that you'll be notified as soon as I upload any new video on my channel. So let us begin today's discussion. Okay, so first let us look at the problem statement. Hydrogen is diffusing through a membrane of vulcanized neoprene rubber 0.5 mm thick at 17 degrees Celsius. The partial pressure of hydrogen on one side of the membrane is 0.010 atmosphere, while at the other end it is 0. Calculate the rate of diffusion per unit cross-sectional area of the membrane. The solubility of hydrogen in neoprene rubber is 0.051 meter cube, that is measured at HTP per meter cube of solid per atmosphere. The diffusion coefficient of hydrogen in neoprene rubber at 17 degrees Celsius is 1.013 into 10 to the power minus 10 meter square per second. Okay. So you have a case where hydrogen gas is diffusing through a membrane. The membrane is made up of vulcanized neoprene rubber. Thickness of the membrane is given to us. Thickness of the membrane is 0.5 mm and temperature is also given to us. The diffusion is taking place at a temperature of 17 degrees Celsius. The partial pressure of hydrogen on one side of the membrane is given. It is 0.010 atmosphere, while at the other end it is 0. While at the other end it is 0. We are supposed to calculate the rate of diffusion per unit cross-sectional area of the membrane. That means indirectly they are saying that the cross-sectional area we are supposed to do the calculation for 1 meter square cross-sectional area of the membrane. The solubility of hydrogen in neoprene rubber is given. The solubility of hydrogen in neoprene rubber is at 17 degrees Celsius. Of course, it is 0.051 meter cube. This volume is measured at STP, at standard temperature pressure conditions, per unit meter cube of solid per atmosphere. That means in 1 meter cube of the solid at 1 atmosphere, 0.051 meter cube is going to dissolve in the membrane at standard temperature pressure conditions, at STP conditions. Then diffusion coefficient of hydrogen in the neoprene rubber is given. So the diffusion coefficient at 17 degrees Celsius, it is 1.03 into 10 to the power minus 10 meters square per second. Okay. So this is the problem statement, and we are supposed to find out the rate of diffusion per unit cross-sectional area of the membrane. Here membrane is the solid through which hydrogen gas is diffusing. ठीक Okay, so first let us note down the given things. Let us note down the data that is given to us. So the case is hydrogen diffuses through a membrane, and we are going to denote hydrogen by A. So A diffuses through a membrane, that is the process. So if it is diffusing through a membrane, that means it is a case of diffusion through a solid slab. It is a case of diffusion through solid slab, and now we know which equation we have to use for calculating the rate of diffusion. So the equation that is applicable to steady state diffusion through solid slab is useful in this case. We have to use that equation. Again, the diffusion is taking place under steady state. The process that is given in the problem statement, the diffusion process, it is occurring at steady state. So we are supposed to find out rate at the steady state. So we can use the equation for steady state diffusion through a solid slab. So that's why I'm saying this is a case of diffusion through a solid slab. Then what else is given? Temperature is given to us. Temperature is 17 degrees Celsius, and we are going to convert that to Kelvin. So it will be 17 plus 273.15, that is equal to 290.15 Kelvin. Then pressure is given, total pressure is given. How much is that? Total pressure is 1 atmosphere. And if you convert that to Newton per meter square, it will be 1.013 into 10 to the power 5 Newton per meter square. Then thickness of the membrane is given to us. In this case, thickness is nothing but length of the diffusion path. I'll show you the schematic, you'll understand. So let me first tell you here, thickness of the membrane is nothing but length of the diffusion path, and therefore I will denote it by Z. So Z is 0.5 mm, which if converted to meter, it will be 0.5 into 10 to the power minus 3 meter. Then after that, solubility of A in neoprene rubber is given. That is, solubility of hydrogen in the neoprene rubber is given. Let us denote it as SA. So SA is 0.051 meter cube at STP per meter cube of the solid. Solid in this case is membrane. So per meter cube of membrane per atmosphere. Solubility is given to us. Then diffusivity of A in the rubber is given, and we denote that by dA. So dA is given as 1.03 into 10 to the power minus 10 meter square per second. Okay, so let us understand the process. So you have the neoprene rubber membrane over here, the membrane. Then thickness of the membrane is 0.5 mm. We have noted over here thickness, that means this dimension of the membrane is 0.5 mm. Let us call this end of the membrane, let us represent that by 1, whereas the other end of the membrane, let us represent it as 2, and diffusion is going to take place from end 1, where partial pressure of hydrogen, it is given to us, it is 0.010 atmosphere. So partial pressure at end 1, I'm denoting it as PA1, partial pressure of A at end 1, this is 0.010 atmosphere, whereas it diffuses to the other end where its partial pressure is 0. That means on this end there is no hydrogen, therefore its partial pressure is 0. That's why the driving force is the partial pressure difference, and hydrogen will be diffusing from high pressure, from the end where its partial pressure is high to the end where its partial pressure is 0. So for this particular diffusion process, we are supposed to find out rate of diffusion. We are supposed to find out rate of diffusion. Okay, so let us move ahead. Now let us solve it. First, for your understanding, uh, we will first write the formula that is to be used in this case. So since this is a case of steady state diffusion through a solid slab, the formula that will be applicable is Ra is equal to dA into A by Z into Ca1 minus Ca2. So we have derived it in our previous video, and over here we are going to use that. Okay, so again you have this the schematic for the process. So concentration Ca1 will be concentration on this end, and Ca2 will be concentration on this end. Right now we don't know Ca1 and Ca2. We have to get it from the information that is given to us. And what is the information that will be useful to us in this case? Partial pressures. So we are supposed to convert Pa1 to Ca1, and since Pa2 is 0, Ca2 will also be 0. So there is no much calculation involved at end 2, but at end 1 we need to convert Pa1 to Ca1, so we have to do that. Okay, so dA is given to us, we have noted that. A is given, rather it is indirectly given, as we are supposed to find out rate per unit cross sectional area. That means A in this case is 1. Then Z is given, thickness of the rubber. That will be the length of diffusion path, because diffusion will be taking place along the thickness. Ca1 and Ca2 are to be calculated. If you have to use this equation, we need to know Ca1 and Ca2. Ca2 is 0 because Pa2 is 0. Ca1 we have to get it from Pa1. So we can now note that there will be two steps in solving this numerical. First step is we have to get Ca1 and Ca2, calculation of Ca1 and Ca2, and second step is Ca1 and Ca2, these are molar concentrations, and this is the first step. And second step is we will be calculating the rate, which is the parameter that is asked in the numerical. Two steps. So first we will get Ca1 and Ca2. Again Ca2 is 0, as you know Pa2 is 0, but we have to get Ca1. So first we will be doing that, and after Ca1 and Ca2 are known to us, we will be using the equation to get the rate. Okay, so let us move ahead. We are supposed to find out Ra, that is rate of diffusion. So first step, as we listed, is calculation of Ca1 and Ca2. So again we will refer the schematic. Ca1, as I said, it is molar concentration at end 1. It is molar concentration at end 1. So please read it as at end 1. Molar concentration at end 1. Ca1, it depends on the amount of A that dissolves in the membrane at 1. So Ca1 will be the concentration at this end, that means after H2 dissolves in the membrane. So whatever will be the concentration of hydrogen after it dissolves in the membrane, that will be Ca1, and that's why Ca1 will depend on amount of A that dissolves in the membrane. So depending on how much hydrogen dissolves in it, that is how much A, we have denoted hydrogen by A, how much A dissolves in the membrane at end 1, that will decide its molar concentration, that is Ca1. The amount of A that dissolves, it depends on its solubility. Clearly it is straightforward. So what, depending on the solubility, hydrogen will be dissolving in the membrane at end 1. The solubility is given to us. What is that? It is 0.051 meter cube measured at HTP per meter cube solid per atmosphere. Meter cube at, so our task is we need to convert this. In the end, we need to have kilomole per meter cube, kilomole per meter cube, because the concentration will be given in, so this is kilomole of H2 per meter cube of solid. So our task is we need to convert meter cube at STP to kilomole at given temperature and pressure. So this is the volume occupied at, or the volume of H2 that dissolves in 1 meter cube of solid at STP. We have to convert it to kilomole of H2 that will be dissolving at given temperature and pressure. Given temperature is 17 degrees Celsius, that is 290.15 Kelvin, and 1 atmosphere. So we have to convert the solubility data to kilomole of hydrogen per meter cube of rubber. This is the task. At STP, pressure is 1 atmosphere and temperature is 0 degrees Celsius. 0 degrees Celsius, that means it is 0 plus 273.15 Kelvin. So these are STP conditions. Okay, so let us do that. Let us learn, let us know how to convert the solubility data to Ca1. Okay, so ideal gas law. Now let us write ideal gas law. How to proceed? To begin with, we are going to write ideal gas law at STP conditions, and we know this fact. What is this fact? At STP, 1 gram mole of an ideal gas occupies a volume of 22.4 liters. So you can check this by solving the ideal gas law. So we know at STP 1 gram mole of an ideal gas occupies a volume of 22.4 liters. That is, I can say 10 to the power minus 3 kilomole. 1 gram mole is 10 to the power minus 3 kilomole. So at STP, 10 to the power minus 3 kilomole of an ideal gas occupies a volume of 22.4 liters, that is 22.4 into 10 to the power minus 3 meter cube. So the known information, I have written it in a different form. So now I know 10 to the power minus 3 kilomole of an ideal gas at STP occupies a volume of 22.4 meter cube. Okay. So now let us use the law. So you have PV is equal to nRT. Pressure is 1 atmosphere. In Newton per meter square it is 1.013 into 10 to the power 5. Volume in meter cube it is 22.4 into 10 to the power minus 3. That is equal to 10 to the power minus 3 into 8314. This is the value of R. So if pressure is, if you are using pressure in Newton per meter square, an amount of substance in kilomole, then value of R will be 8314. So you have to be specific, rather you have to be careful while using value of R. So now since I am using pressure in Newton per meter square and amount of substance in kilomole, so for these cases value of R will be 8314, and I am calling this as equation 1. If you check the equation, every term is known to us, but still I have written the equation and I am calling that as equation 1. Okay. Now next what I do, I will use ideal gas law at given conditions. What are given conditions? Pressure is 1 atmosphere and temperature is 17 degrees Celsius, that is 290.15 Kelvin. Now we will write ideal gas law. Of course, while writing this law, we are assuming that hydrogen is behaving as a ideal gas. There is no, that is an assumption. Okay. So ideal gas law, now if it is written at given conditions, what are the given conditions? Pressure is 1 atmosphere and temperature is 17 degrees Celsius. So at given conditions, if you write pressure is rather here pressure, we are, since we are writing it for hydrogen, pressure will be its partial pressure at end 1. If you remember the schematic, you had the membrane, and on this end partial pressure of hydrogen was 0.01 atmosphere. We had denoted that by PA1, so that was 0.010 atmosphere. This was the partial pressure, and now we are applying this law to hydrogen gas. So that's why partial pressure is 0.010 atmosphere, and now I'm converting it to Newton per meter square. So that's why I have to multiply. In order to convert it to Newton per meter square, I'll have to multiply with 1.013 into 10 to the power 5. Okay. So this particular product, this product 0.01 into 1.013 into 10 to the power 5, this will be partial pressure of hydrogen in Newton per meter square. Okay, into 0.051, this is the volume that is occupied by hydrogen, and we need to find out if this volume is to be occupied at given conditions. What is given to us as per the solubility data, you have 0.051 meter cube of hydrogen at STP occupies per meter cube of solid per atmosphere. Now we are converting it to kilomole. Okay, so at given conditions, the law will be written like this. So this many meter cube of hydrogen, that is equal to, we don't know how many kilomoles of hydrogen will occupy this volume at given conditions. So that's why I'm saying it is X into R8314, because pressure is in Newton per meter square and amount of substance we are considering in kilomole, into given temperature is 290.15 Kelvin. Okay, so I hope this is clear to you. You have partial pressure of hydrogen into volume it will be occupying at given conditions, and for this volume, if what is the kilomole of hydrogen that will occupy this volume at given conditions of temperature and pressure. Pressure is 1 atmosphere total pressure, but temperature is different. Temperature is 290.15 Kelvin. Are you understanding it? So once again, let me tell you, we are considering hydrogen gas that has this much partial pressure. Why this much? Because it is given to us. On this side, partial pressure is 0.010 atmosphere, and by multiplying it with 1.013 into 10 to the power 5, we are converting atmosphere into Newton per meter square. So hydrogen gas with this partial pressure and which occupies a volume of 0.051, what will be kilomoles of that hydrogen at a temperature of 290.15 Kelvin. So basically we are supposed to get X, and now I call this as equation 2. So if you don't, if you're not understanding, if you have any doubt, you please mention that in the comment section, we will discuss that. ठीक है. So after writing ideal gas law at STP, I got equation 1, and after applying ideal gas law at given conditions with given partial pressure of hydrogen, I got equation 2. Now in the next step, what I am going to do, I will be dividing equation 1 with equation 2, so that in the end I will have one equation in X. Okay, so that is what I have done on the next slide. So you can check again with the same step. From the previous slide we had those two equations. I have rewritten those two equations. 1.013 into 10 to the power 5 into 22.4 into 10 to the power minus 3, that is equal to 10 to the power minus 3 into 8314 into 273.15, that is equation 1. And now equation 2 is 0.013 into 1.013 into 10 to the power 5 into 0.051 into x, that is equal to x into 8314 into 29015.15, that is equation 2. Now let us take ratio, that is, let us divide 2 with 1. So on the right hand, on the left hand side, you'll have 1.013 into 10 to the power 5 into 22.4 into 10 to the power minus 3 divided by 0.010 into 1.013 into 10 to the power 5 into 0.051, that is equal to 10 to the power minus 3 into 8314 into 273.15 divided by x into 8314 into 290.15. So after simplifying, you get this equation: 43.92 is equal to 9.41 into 10 to the power minus 4 divided by x, and now you have to get x. So x will be 9.41 into 10 to the power minus 4 divided by 43.92, and that comes out to be 2.14 into 10 to the power minus 5 kilomole. That means 2.14 into 10 to the power minus 3 kilomole will occupy a volume of 0.051 meter cube at the given conditions, at a pressure at a pressure that is equal to partial pressure on N1, and at temperature of 17 degrees Celsius. In short, we have converted the solubility data to kilomole at given conditions. Okay, so x we are getting is 0.14 into 10 to the power minus 5 kilomole. Okay, now we are close to getting Ca1. Now let us. Okay, so on the previous slide we got x. X was 9.41 into 10 to the power minus 4 divided by 43.92, which is 2.14 into 10 to the power minus 5 kilomole. That means now we have converted SA, that is solubility, which was 0.051 meter cube at STP per meter cube solid per atmosphere, to kilomole per meter cube of solid. So now solubility is 2.14 into 10 to the power minus 5 kilomole of hydrogen per meter cube of solid at the given conditions. So this is nothing but Ca1. So Ca1 is 2.14 into 10 to the power minus 5 kilomole per meter cube per solid. So again you have this schematic. Now Pa1 is converted to Ca1. On the other side, Pa2 is 0. That means Ca2 is also, Pa2 is 0. That means there is no A, that is hydrogen on at in2. So that means Ca2 is also equal to 0. Okay, so this ends step number 1. So I have discussed this step in details. When you actually solve this problem, you can do it by omitting some steps. I have discussed those steps over here. so that you can understand. Now we have CA1 and CA2. Now let us go to step 2. In step 2 we are supposed to calculate rate. For this we are going to use this equation. Now everything on the right hand side is known to us, so that we can get RA. So dA is known, it is 1.013 into 10 to the power minus 10 meter square per second. A is 1 meter square, since rate is to be calculated per unit area. Z is known, it is 0.5 mm, that is 0.5 into 10 to the power minus 3 meter. CA1 we calculated 2.14 into 10 to the power minus 5 kilomole per meter cube per solid. Ca2 is 0. So if you keep all the values, so you have dA is 1.013 into 10 to the power minus 10, area is 1, Z is 0.5 into 10 to the power minus 3 into 2.14 into 10 to the power minus 5 minus 0. So if you do the calculations, you will get RA as 4.41 into 10 to the power minus 12, and now unit will be kilomole per second per meter square, and that is the final answer that is expected in this case. So rate of diffusion per unit cross sectional area of the membrane is 4.14 into 10 to the power minus 12 kilomole per meter square per second. So with this we complete, we have the solution for this problem, and with this I complete my discussion for this video. In my next video I will discuss one more numerical that is based on diffusion in solids. So for today it is finished. You please subscribe to my channel, tell your friends to subscribe to my channel, hit the bell icon so that you'll get notified as soon as I upload any new video. For now, bye, have a nice day, and keep watching my videos. Thank you for being with me.